Chapter 9 is going to focus on nuclear chemistry. What we have been dealing with up to this point has been chemical change. And when you're dealing with chemical change, that's going to involve the electrons and what's happening on the outside of the nucleus. Now we're going to talk about nuclear change, and that involves changes that are occurring inside the nucleus. There's a lot of natural radioactivity going on around us, so this picture is good. This guy's just heading off to school, not necessarily aware of all the radiation that is hitting his body. So we'll talk a little bit more about shielding and protection from radiation in some later slides. Nuclear radiation is radiation that is emitted by unstable atoms. They take the form of radiation such as alpha particles, neutrons, beta particles, positrons, and gamma rays. So this table has a lot of information on it, so we're going to focus on, I'm just going to go down each one to talk about them. But for starters, this second column right here is giving us a symbol that's the elemental particle symbol. So when you're doing your homework, there's some of the problems that say, put in the elemental particle, put it in as the elemental particle, and other times it'll say put in the symbol as a nuclear symbol. So I just wanted to point out the difference when you're doing the homework. So the first one here to look at is the alpha particle. It has the Greek letter alpha. It also is, if we're talking about the nuclear symbol, it has 2 protons and 2 neutrons. So if you remember back previously when we talked about nuclear symbols, you put the atomic number in the lower left-hand corner, and the top left number is the mass number, and the mass number is the number of protons plus neutrons. So an alpha particle has 2 protons and 2 neutrons, so the mass number is going to be 4, which is why we have a 4 in the upper left-hand corner here. So this is the nuclear symbol for an alpha particle. Mass number is 4, and it has a charge of 2+. So it is a highly charged particle. The beta particle, once again, the elemental symbol is the Greek letter beta. Here is the nuclear symbol. So and I do want you to have these memorized, the symbols of these different types of radiation. Nuclear symbol is this lowercase e, with a -1 is the atomic number. So that's a little different because the atomic number usually stands for how many protons. And a beta particle doesn't have any protons. It's basically an electron that comes out from the nucleus. Now that should surprise you because you should be saying, whoa, Bernadette, you never taught me there was any electrons inside the nucleus. It's just protons and neutrons. Well, what they say, the way they explain that is they say that a neutron changes into a proton by emitting an electron. So if we say we have a neutron which is neutral, if it gives off a negative particle similar to an electron, well then it's going to be left with a positive charge. So that's why they say the neutron turns into a proton. Okay, and so then the mass number is going to be 0 because there is no protons, and the charge is a -1 because a beta particle is very similar to an electron. You can also lose a positron from the nucleus. And here is the elemental particle symbol for a positron, and this is the nuclear symbol for a positron. And the way they describe a positron coming out of the nucleus is they say that a proton changes into a neutron, and then the positron's emitted. So if you think about the proton, it has a +1 charge. If it loses a particle that carries away that positive charge, then what you're left with is basically a neutron. It has a mass number of 0 and a charge of +1. Focusing on the gamma ray, this is the Greek letter gamma, lowercase letter for gamma. Here would be the nuclear symbol. Basically, gamma is just energy. It's not even considered a particle. So it doesn't have any protons or any neutrons, so that's why the nuclear symbol would have 0s there. Basically, it's just energy lost to help stabilize the unstable nucleus. Mass number 0, and it has no charge, it's just energy. Proton, we're already familiar with. The symbol is a lowercase p. If we're talking about it in a nuclear symbol, we give it that, the hydrogen nucleus, where it has 1 proton and then the mass number is 1 because it doesn't have any neutrons. So it's just a proton being emitted from the nucleus. Mass number is 1 and the positive charge of 1 because it's just your basic proton. And then here's the symbol for the neutron, lowercase n. If I wanted the nuclear symbol for a neutron, it's going to have 0 protons but a mass number of 1, because 1 neutron, 0 protons is going to sum up to 1. And then the change in the nucleus is that a neutron is emitted. The mass number is 1. Oh yeah, we've covered that. And then there's no charge. So this is just kind of a summary, again, of some of those particles that I just had on the previous slide. The alpha particle is 2 protons and 2 neutrons, so there's the nuclear symbol. Beta particle is a high energy electron, so it has this symbol with a -1 down here, kind of symbolizing that it has the negative charge. A positron is a positive electron, so that's why you'll see it with this negative symbol, but it has a +1 here. A gamma ray is just high energy radiation released from the nucleus when it decays, and so there's our nuclear symbol. So make sure you have these 3 particles memorized. So stable versus radioactive isotopes. If we look at this table has, the first column is showing magnesium, and you can see that magnesium 24 is actually a stable isotope of magnesium. It doesn't undergo radioactive decay, but magnesium 23 and magnesium 27 are unstable, and so they will go through radioactive decay. Iodine 127 is stable, but iodine 125 and 131 are radioactive. Uranium doesn't have any stable isotopes. And here's uranium 235, and they're showing uranium 233 as examples of some of the radioactive isotopes of uranium. So a radioactive isotope has an unstable nucleus. It's going to emit radiation to become more stable, changing the composition of the nucleus. A radioactive isotope is identified by the mass number of the isotope. So if you're trying to convey to somebody what particular isotope of an atom you're talking about, you have to give them the mass number. Because remember, that's our definition of isotopes. Isotopes have the same atomic number but different mass numbers. So you can convey a mass number to a reader these 2 different ways. You can either write the name of your element with a hyphen followed by the mass number, or you can give the nuclear symbol, because chemists all have memorized that the mass number is in the upper left-hand corner. So that's another way of conveying the mass number to the reader. So this is a refresher. I pulled this slide from a previous chapter just so we can remember how to do this. So from the nuclear symbol, and once again, when I'm asking you for a nuclear symbol, I want the mass number in the upper left-hand corner and the atomic number in the lower left-hand corner. So from the nuclear symbol, we can determine the number of protons, neutrons, and electrons in a particular atom. And so here's our example. If we focus on the oxygen 16, the atomic number in the lower left-hand corner tells us the number of protons. And so we can say that just by looking at this 8, that there's 8 protons. If I go down here below to go over these last 2 bullets before we go on, atoms are electrically neutral. So all 3 of these examples are atoms. The way I know that is that there's no charge written in the upper right-hand corner. That's where we put the ion charge if we're talking about an ion. So since there's no ionic charge out here, that would imply we're talking about a neutral atom. So the number of protons is going to equal the number of electrons if we're in an atom. Also, the number of protons in the nucleus determines what atom it is we're talking about. So remember, you get the atomic number from going to the periodic table and saying, oh, oxygen has 8 protons. So it is the number of protons that identifies what atom we're talking about. Okay, so to answer how many protons and electrons there are, that's really easy. We just look at the lower left-hand number and we say there's 8 protons, 8 electrons. To determine out the number of neutrons, we actually have to do a subtraction. Since the mass number is protons and neutrons, and the atomic number is just protons, if you subtract the atomic number from the mass number, that's going to give you the number of protons. So 16 minus 8 is 8. That's how we come up with 8 neutrons. If we look over here at phosphorus, I can see right off the bat there's 15 protons and 15 electrons. And then I go 31 minus 15 is 16, so that tells me there's 16 neutrons. So here's a learning check. From the following nuclear symbol, determine the number of protons, electrons, and neutrons in the magnesium isotope. Okay, so It's asking for protons, electrons, and neutrons. Notice I did that very carefully. I read this very slowly. I went protons, electrons, and neutrons. Okay, sometimes I get students who get the problem wrong because they get in the habit of always going protons, neutrons, electrons, because that's how the previous slide was. So I mixed this up on purpose. So the number of protons is just going to be my atomic number, so that's 12. The number of electrons is going to equal the number of protons because I don't have any charge out here. In this chapter, we're not going to be dealing with ions. So for the most part in nuclear chemistry, you just focus on the neutral isotopes. Okay, to determine the number of neutrons, I have to do a subtraction here. So 3 minus 2 is 1, 2 minus 1 is 1, so that means there is 11 neutrons in this particular isotope. The second question, how many higher here, protons, neutrons, and electrons are in magnesium 27. So when it's me, I prefer to actually write out the nuclear symbol. It's telling me it's magnesium 27, which means I have 27 in the upper left-hand corner. I look at my periodic table to find out that the atomic number of magnesium is 12. So once I figured out the atomic number is 12, then I know the protons and electrons are 12. The neutrons on this case, I'm going to do a subtraction. So 7 minus 2 is 5, and then I get 1, so I have 15. All right. So how do we shield ourselves from radiation? So what shielding helps give radiation protection? So first of all, we're going to focus on the alpha particles, beta particles, and gamma rays. It turns out that if we're talking about how far these particles can travel through air, so if you have your radioactive material and it's giving off an alpha particle, that alpha particle actually is only going to go about 2 to 4 centimeters in the air. So how far they travel in the air. Beta particles can travel about 200 to 300 centimeters, and gamma rays can go for 500 meters. So they actually can travel pretty far. If we're talking about how the depth into our tissues they can go, an alpha particle cannot go very far, barely at all, into skin tissue. So this is what, 5/100ths of a millimeter, and if you can think about a ruler, how tiny a millimeter is. Beta particles can go about 4 to 5 millimeters through skin tissue, and gamma rays can go about 50 centimeters or more, so they can just travel right through your skin. So what can shield these radiations? Well, it turns out that paper or clothing is enough shielding to block your alpha particles. Heavy clothing or lab coats and gloves are enough to stop any beta particles. And you would need lead, which is one of the most dense metals. You need lead or really thick concrete if you want to stop a gamma ray. And then here's just some typical sources of those three. So radiation protection, a little more on this. So if you want to protect yourself from radiation, it's going to require paper or clothing to stop the alpha particles, a lab coat or gloves to stop beta particles, lead shield or thick concrete wall will stop your gamma particles. Another way to protect yourself from radiation is you can just limit the amount of time that you spend around that radioactive source. So time, it will definitely play a role in how much you're exposed to the radiation. Another thing you can do is you can increase the distance from your radioactive source. Because remember, some of them don't travel very far through air. So if you just back up from the source, then it's not going to penetrate. So here's the learning check. What type of radiation will be blocked by the following? So A is saying what type of radiation is going to be blocked by lead shielding. You can kind of interpret this question different ways. I think they're really getting at that lead shielding is what's used to stop a gamma ray. But technically, lead shielding could also stop an alpha particle and a beta particle. There's no way they're going to penetrate through lead because paper can stop, alpha particles. What radiation can be stopped by paper or clothing? That would be our alpha particle. So radiation measurements. This is showing a man holding a Geiger counter, and he's reading how much radiation this ground is giving off. So a little bit about the Geiger counter. It detects beta and gamma radiation. it uses the ions produced by the radiation to create an electric current. So here is our radioactive source in this picture, and it's giving off a particular radiation. And inside of our detector here, it's the radiation is causing ions to form. Those ions are causing an electric current to happen, which the Geiger counter then can then interpret for us as to how much radiation is being given off. Some units that we use for radiation. A curie measures the activity of the number of atoms that are decaying per second. A RAD is the acronym for radiation absorbed dose, and it measures the radiation absorbed by the tissues of the body. Where a REM is another unit you'll see on radiation, and it stands for the radiation equivalent, which measures the biological damage caused by different types of radiation. So if you go on to any type of allied health field where you're dealing with radiation, you might see these units on numbers. And if you see this unit following a number, then you're going to know it's a type of radiation. So exposure to radiation occurs from naturally occurring radioisotopes. So we have back in the lab room, in the stock room, we have some pottery that is covered with some orange paint. And that was back before they realized how much radioactive isotopes were in some of the paints that they were using. So we actually can take the Geiger counter over some of this pottery and see how much radioactivity is being given off. So there's a lot of just natural rocks and ore that is just naturally decaying and giving off radiation. You also can get exposed to radiation from medical and dental procedures. Air travel. Radon. Radon is one of your noble gases that is a natural decay product of like uranium and thorium. When they in the ground naturally are decaying, radon is one of the elements or isotopes that they decay into, and then radon itself is radioactive. So smoking cigarettes exposes you to radiation. And then cosmic rays also expose our bodies to radiation. Some of these are pretty interesting. I kind of want to look down this table with you for a little bit because I found some of them pretty surprising. Here we've got some natural sources of radiation. So just the ground itself, depending upon where you are, but you might be more exposed to more ore that might be radioactive. So average dose might be about 20 millirems. Your air, water, food, you can get about 30 millirems of radiation from. Cosmic rays that we're exposed to give us about 40 millirems. Wood, concrete, brick, about 50. So out of the natural sources, that's giving us the most, the wood being around concrete or brick walls. Focusing on medical, an x-ray is going to give you about 20 millirems. Dental x-rays about 20. That was comforting me when I saw that because the 20 here is about what you're exposed to just from, from some of the ground that you might be around. Mammograms give you about 40 millirems. A lumbar spine x-ray 70, upper gastrointestinal tract x-ray is 200. So that one comes with quite a bit of radiation. So some other sources, this one might surprise you. If you're standing outside a nuclear power plant, you might be thinking, ooh, I don't want to get very close to this nuclear power plant because of all the radiation that's probably I'm being exposed to, and that's not really true. You'd end up being exposed to 0.1 millirems of radiation. Air travel gives you about 10 millirems. Television, 20 millirems. Here's radon. We've got an asterisk saying it varies widely depending upon, where you're taking your sample from. Okay, focusing a little bit on the half-life of radioisotopes. The half-life and the decay curve is what I'm showing you on this slide here. So the half-life of a radioisotope is the time for the radiation level to decrease or to decay to half of the original value. So if we look at this graph here, which is telling us is a decay curve for iodine-131. So if we look at it, they're starting off with at time equals 0, so 0 days, we start off with 20 milligrams of iodine-131. And they start letting it decay, and when you get to half of 20, that puts us at 10. So it took 8 days for my sample to cut in half. So it went from 20 down to 10 and it took 8 days to do that. So we say the half-life of iodine 131 is 8 days. You could really start anywhere on this graph. We could have started off here at the 10 and said, well, half of 10 is 5. So how long did it take for it to go from 10 milligrams to 5 milligrams? So 10 milligrams were right here, 5 milligrams were right here, and once again you can see 8 days passed. So the half-life of iodine 131 is 8 days. Here's some half-lives of just some radioisotopes. Here we've got some that occur naturally. Down here we have some that they use for medical diagnostic purposes. Some of them, let's just point some out. Carbon-14, which is what is carbon dating. When you carbon date how old an object is, you might use carbon-14. That has a half-life of 5,730 years. If we look at uranium-238, this has a half-life of 4.5 billion years. So it takes 4.5 billion years for your sample of uranium-238 to just get cut in half. And then it's going to take another 4.5 billion years for that sample to get cut in half. So you can go over this slide by yourself. I wouldn't ask you any test questions related to the specifics of this slide, but you can look at what type of radiation they give off. Some of them give off beta particles. Potassium-40 not only gives off beta particles, but it gives off gamma rays at the same time. So you can look over that slide if you're interested. How we're going to do some half-life calculations, so I've got a couple examples for you. The radioisotope strontium-90 has a half-life of 38.1 years. If a sample contains 36 milligrams, how many milligrams will remain after 152.4 years? Now, I'm going to set these up. I like to do this like arrow diagram, where you start off with how much of your radioisotope you have. So we're starting off with 36 milligrams of strontium-90. And I'm going to do this arrow representing one half-life. So one half-life has transpired, so how much will I have left after one half-life? Well, we always have half. So you cut 36 in half, and that's 18 milligrams. If I go through another half-life, 18 divided by 2 is 9 milligrams. So I like to keep going until I get to where I need to stop. Well, this question is asking me how much I'm going to have left after 152.4 years. So I have to figure out how many half-lives, how many arrows I'm going to need. So what I need to do, so I'm going to kind of digress here for a second, to figure out the number of arrows, just in case you want to use this method, that's going to equal your total time divided by the half-life. So in our case, the total time that occurred was 152.4 years, and the half-life is 38.1, and that is going to equal 4 years. So it went through 4 half-lives. So I'm going to need 4 arrows. So I have to cut the 9 in half, and that's going to be 4.5 milligrams. So right now I've gone through 3 half-lives. I've cut it in half 3 times, but I have to cut it in half one more time, so that's going to be 2.25 milligrams. So that is how many milligrams I have left after 152.4 years has gone by. What is the, okay, so the half-life of iodine 123 is 13 hours. How much of a 64 milligram sample of iodine 123 is left after 26 hours? So let's go ahead and do this again. Let's start off with how much we have. We're starting off with 64 milligrams. And I'm going to cut that in half. And I'm going to end up with 32 milligrams. But I don't want to keep going. I have to figure out how many I'm going to keep going. So let's do how many arrows we need. So we take our total time, which is 26 hours, and we divide it by 13 hours. You have to make sure you have the units all the same, okay? So that is going to end up being 2. So we have to go through 2 half-lives. So if I go through 1 half-life, I've got 32 milligrams. 2 half-lives is going to be 16 milligrams. So the answer to this question is going to be B. Here it says, how old is a sample of wood whose carbon-14 content is found to be 25% of a living tree? So if you have a living tree, it's going to have 100% of the carbon-14 that living wood would have. But this piece of wood that they found only contained 25% of carbon-14. So 75% of the carbon-14 had disintegrated, it had decayed. So the half-life of carbon-14 is 5,730 years, and it wants to know how old this tree is. So let's start off just by thinking about half-lives in terms of percents. If I start off with 100%, and it goes through one life, what half-life, what percentage do I have left? So I'm only going to have 50% of my sample left after the first half-life. When it goes through another half-life, then I'm only going to have 25% of my original sample. And you can keep going. So this tells me that I only have 25% of my carbon-14 left. So it must have gone through 2 half-lives. So after the first half-life, to go to 50%, 5,730 years passed. The second half-life, another 5,730 years. So I just have to add this up, and I end up with my 11,460 years is how old we'd say that piece of wood is, approximately. All right, so some medical applications using radioactivity. Radioisotopes with a short half-life are often used in nuclear medicine because they have the same chemistry in the body as your non-radioactive atoms in the body. They also, in the organs of the body, they give off radiation that exposes a photographic plate, which we then use, we call the scan, giving an image of the organ. So here are some isotopes used in radioactive diagnostic tools, and it gives the half-life of some of them. This first one's kind of interesting, and you might not realize you use gold if you're trying to image the liver or treatment for abdominal carcinoma. See if there's any other interesting ones in here. It's kind of interesting to look at the half-lives of them. This guy right here, fluorine 18, is a positron emission, and it's used in this type of topography. So I'm not quite used for what part of the body it's used to scan, but its half-life is 110 minutes. So it's a kind of short one. Gallium 68 has a fairly short half-life. It's a gamma emitter used to detect pancreatic cancer. So you can look over this if you're interested in it. I wouldn't ask you anything as specific as this, but some of them are pretty interesting. So scans with radioisotopes. After the radioisotope is ingested by the patient, the radiologist is going to determine the level and the location of the radioactivity being emitted by that radioisotope that is now in the patient's body. The scanner is going to move very slowly over the organ where the radioisotope was absorbed. And then the radiation emitted from the radioisotope can be used then to expose your photographic graph, giving us a scan of the organ. So here's a picture of a scan. I would have no knowledge as to how to read a scan like this, but some of you might be taking this class because you're going to go in to be an X-ray technician or something like that. So you'll have to come back and teach me how to read this slide one of these years. So a scanner is used to detect the radiation from a radioisotope that has accumulated in the organ. It looks like this lady perhaps is getting her thyroid scanned. B is a scan of the thyroid, shows the accumulation of radioactive iodine 131 in the thyroid. Okay, that's pretty cool. So here's a learning check. Which of the following radioisotopes are most likely to be used in nuclear medicine? So do you think that they're going to use potassium-40, which has a half-life of 1.3 billion years? Well, how many of us want to walk around with a radioisotope in our bodies that long? So we would not want A. So the main point of this slide is testing your knowledge that you tend to want your shorter lived isotopes with a short half-life to be used in your diagnostic tools. So I would say iodine 131 is going to be our best bet because it has a half-life of 8 days. But 12 hours isn't so bad either. So